You go through it. It is also a similar kind of problem as that of previous problems. A rectangular beam of span 8 meter is 150 mm wide and 300 mm deep. Cross-sectional dimensions are given. The beam is prestressed by a parabolic cable having an eccentricity of 75 mm below the central axis at midspan and 25 mm above the central axis at support sections. Okay, write the diagram. Solution. So beam span is 8 meter and it is 150 mm wide and 300 mm deep. Okay. Eight meter span. L is equal to 8 meter. Correct. L is equal to 8 meter. Cross section is 150 by 300. Let me write the cross section as well here. (150 by 300). Then prestressed by a parabolic cable having an eccentricity of 75 mm below the central axis at midspan and 25 mm above the central line at support sections. First write the central axis so that we can write the cable profile as per the given problem. What it says is it is having 75 mm below the central axis at midspan eccentricity and 25 mm above the central axis at support sections. And it's a parabolic cable. Okay, you write the cable profile accordingly as per the given problem. Yes. Here, eccentricity is 75 mm at midspan below the central axis. At support, the eccentricity is 25 mm above the central axis. 25 mm. Okay. Now, moving ahead with reading the problem. The initial force in the cable is 350 kilonewton. Prestressing force is given. P is equal to 350 kilonewton. P is equal to 350 kilonewton. Then the beam supports three concentrated loads of 10 kilonewton each at intervals of 2 meter. Three concentrated loads of 10 kilonewton each at an interval of 2 meter. Means at every 2 meter interval along the length of the beam, there are three concentrated loads having magnitude of 10 kilonewton. Let me apply those loads at 2 meter interval. From 0 to 2 meter, there is one load. And 2 to 4 at 4 meter, there will be one load. And at 6 meter, there will be one more load having magnitude of 10 kilonewton. 10 kilonewton and 10 kilonewton. Okay, here 2 meter is the interval. 2 meter, 2 meter and 2 meter. Okay, then Young's modulus of concrete is given EC. EC is given as 35 kilonewton per mm square. EC is equal to 35 kilonewton per mm square, which is equal to 35 into 10 power 3 Newton per mm square. Correct? Then neglecting losses of pre-stress, estimate short-term deflection due to self-weight and pre-stress. That is the first question. And allowing for 20% loss of pre-stress, estimate the long-term deflection. Okay, for pre-stress plus self-weight plus live load. Okay, creep coefficient is also given. Okay. Now initially we will solve the first problem, neglecting the loss of pre-stressors, estimate the short-term deflection due to self-weight and the pre-stress. Means we have to find initially the deflection due to self-weight, then deflection due to pre-stress individually we have to find. Adding together we will get short-term deflection. Correct? Now first you find deflection due to dead load. First one, deflection due to dead load. Deflection due to dead load. Okay. We have the formula. So before that you find dead load of the beam. Cross section is given. Dead load intensity of beam is equal to cross sectional area multiplied by density. Correct? So cross sectional area is given as 150 by 300, nothing but 0.15 into 0.3 into density of PAC is 24, which gives the dead load intensity of 1.08 kilonewton per meter. Okay. Now you can find deflection due to dead load. We have the formula, that is 5 by 384 W L raised to 4 by EC into IX is the formula. Okay. And IX is also required for calculating the deflection. You find the IX. We have the formula for finding the moment of inertia of the rectangle section, that is BDQ by 12. BDQ by 12. B is 150. D is 300 cube divided by 12. You will get 337.5 into 10 power 6 mm raised to 4 as moment of inertia. Therefore, deflection due to dead load is equal to 5 by 384 into intensity of the dead load is 1.08 kilonewton per meter. In terms of Newton per millimeter, it is same only, Newton per millimeter. If you convert it into Newton per millimeter, you will get the same value. Correct? Therefore, delta D is equal to 5 by 384 into 1.08 into length of the beam is given as 8 meter. 8 meter means 8000 mm. Correct? 8000 raised to 4 divided by EC into IX. EC is 35 into 10 power 3. 35 into 10 power 3 into IX is 337.5 into 10 power 6. Therefore, deflection due to dead load is given by 4.49 millimeter. If you calculate the answer, you will get the answer as 4.49 millimeter. All of you check the answer, calculate all of you, and check whether you are getting the same answer or not. Okay. If you are getting any other different answer, let me know. Okay. Now we have estimated deflection due to dead load. Similarly, we will estimate deflection due to live load. B, deflection due to live load, delta NL. Okay. Now to find deflection due to live load, the live load, how it is given? It is 3-point loading is given. 10 kilonewton is the magnitude of the force. Okay. So if I go through the theory part of this particular model, we don't have the formula for that kind of loading, live load. Correct? Deflection due to live load. Let me go to the beginning of the theory part of this deflection. Yes, here we have deflection due to dead load. Okay, then deflection due to live load. For UDL, simply supported beam carrying UDL, we have the formula 5 by 384. For simply supported beam carrying point load at the midspan, we have the formula WLQ by 48 EI. Okay, for 2-point loading also, we have the formula 23 by 2 648 into WLQ by EC into IX. Similarly, for cantilever beam also, we have the formula. Okay, so here we have the case similar to this problem. Okay, it is also 3-point loading. It is also 3-point loading. Either you can use this WLQ by 48 EI formula. Sorry. Either you need to use this generalized equation only. Correct? You need to use this generalized equation only. This is here I have derived the equation for this case. Point load carrying simply supported beam. Okay. So what you have to do? Well, first you need to generate bending moment diagram. Okay. You need to generate the bending moment diagram. For that bending moment diagram, using this generalized equation delta is equal to area into x bar divided by EC into IX, you have to identify deflection due to, you have to find deflection due to the live load. Okay. So the first step is what? To find the bending moment diagram for the live load. Okay. Bending moment diagram for the live load. If standard equations are available like this, okay, like 5 by 384 W 1 by 48 into WQ by EC into IX. If standard equations are available, you can utilize the equations or you can directly get the deflection value. If standard equations are not available, if different loading condition like this 3-point loading is given, then you need to follow the generalized procedure. General procedure is what? Initially to find the bending moment diagram due to the live load. Using that bending moment diagram, using this generalized equation delta is equal to area into x bar by EC into IX, you need to find the deflection. Okay. Now live load is 10 kilonewton 3-point loading at 2 meter interval. Let me write the diagram. Okay. Here 10 kilonewton and 10 kilonewton and one more 10 kilonewton. So interval is 2 meter, 2 meter, 2 meter, 2 meter and 2 meter. Okay. Now for this loading condition, we have to develop BMD or bending moment diagram. Okay. Now we'll develop the bending moment diagram using the first principle, means finding the reaction at the support and finding bending moments at each and individual points and writing the bending moment diagram. Okay. Now first you find reactions at the supports. Let me call this as point A, this as point B. Okay. Or else we'll call as point A, B, C, D and point E. Okay. Now reaction at A and E you find first. Reactions at support is equal to, see here you can see it is a symmetric loading. The loading is symmetric. Okay. If the loading is symmetric, the reactions at A and E will be the same. The reactions will be same, means the total load on the beam, which whatever it is acting, it will be equally distributed to both the supports. That is the meaning. Okay. If unequal loading is given, then you need to find reactions using the equilibrium equations. Okay, that is sigma Fi equal to 0, sigma Ma is equal to 0. Using those equilibrium equations, you need to find the reactions. Here the loading is symmetric. As the loading is symmetric, then directly the reactions at A and E will be total load divided by 2. As the loading is symmetric reaction at A, reactions RA and RE. RE is equal to total load divided by 2. Okay, total load is 10 plus 10 plus 10 divided by 2. Therefore, RA is equal to RE is equal to 30 by 2, 15 kilonewton. 15 kilonewton. Let me write those reactions here so that it will be helpful to calculate the bending moments at required points. Here, 15 kilonewton, RA is equal to 15 kilonewton and RE is equal to 15 kilonewton. Now you can find bending moment at each and every point. Bending moment at A is equal to bending moment at A is equal to 0 because simple support. Okay, at simple support, the moment will be 0. Okay, then you find bending moment at B. Bending moment at B is equal to MA is equal to 0. MB is equal to bending moment at B is equal to at this point 15 into 2, 15 into 2 meter, that is 30 kilonewton meter. Okay, then bending moment at C, bending moment at C is equal to MC is equal to moment of this reaction about point C is 15 into 4 meter minus 10 into 2 meter. Okay, so 15 into 4 plus 15 into 4 minus 10 into 2. Okay, why plus 15 into 4? Because this 15 kilonewton reactive force will cause positive bending moment, means clockwise bending moment about point C. That is why sign is plus. Coming to this 10 kilonewton load, this 10 kilonewton load will cause negative bending moment, means it will cause anti-clockwise moment about point C. That is why minus. Okay, 15 into 4 minus 10 into 2. So you will get the answer as 40 kilonewton per meter. 40 kilonewton per kilonewton meter. In terms of Newton millimeter, it is 30 into 10 power 6 Newton millimeter. Here it is 40 into 10 power 6 Newton millimeter. Okay. So as the loading is symmetric, whatever the moment you got at point B, same moment will be there at point D. Okay. And whatever the moment at A, same moment will be there at point E. That is 0. Okay. Now you can write the bending moment diagram. Draw the reference line first. Moment at A is 0. Correct. Moment at B is 30 into 10 power 6. 30 into 10 power 6. Then moment at C is 40 into 10 power 6. Into 10 power 6. Same value will be there at point D. That is 30 into 10 power 6 and 0. Okay. Join the points. This is what the bending moment diagram. Okay. Now consider half of the portion of the diagram for the calculation. For the calculation. Okay. Let me share the half of the diagram, bending moment diagram. Okay. Now by utilizing this generalized formula, okay, that is delta is equal to we know that delta is equal to, now we are finding delta due to live load. Okay, deflection due to live load is equal to area into x bar divided by EC into Ix. Okay, using this formula we have to find the deflection. Okay, here first what we have to do is we have to segregate this whole area into simple components, means regular components. Okay, now what I will do, I'll take this triangle as component number 1. Okay, now this figure I'll divide into one right angle triangle and one rectangle. Okay, I'll take this rectangle as component number 2 and this right angle triangle as component number 3. Component number 3. Okay. So positive bending moment only. Okay. Bending moment will be positive only. Now expand this generalized formula with respect to this particular bending moment diagram. There are 3 components. So if we expand this formula, it will be A1 x1 bar plus A2 x2 bar plus A3 x3 bar all divided by EC into Ix. Okay. Now you find A1, A2, A3 and x1 bar, x2 bar and x3 bar. Okay. First A1 area of component 1 means area of triangle 1. Okay. Here it is. The distance is 2000, 2000. Okay. So area of this rectangle triangle is half into base into height, half into 2000 into 30 into 10 power 6. Half BH, half into 2000 into 30 into 10 power 6. Okay. Answer which you get is 6 into 10 power 10. Okay. Is the area. Sorry. 3 into 10 power 10. It is 3 into 10 power 10. Then coming to the x1 bar, x1 bar is nothing but here it is distance of centroid of rectangle 1 from the nearest support is x1 bar. Similarly for rectangle 2, distance of centroid of rectangle 2 from nearest support is x2 bar. Okay, similarly here you will get, if you take G3 as centroid of rectangle triangle 3, then x3 bar will be here. Okay. Now A1 is over, x1 bar will be how much here? Okay, it will be 2b by 3, correct? Distance of centroid of right angle triangle from this end point is at a distance of 2b by 3 distance. 2b by 3 here, 2b by 3, which is equal to 2 into 2000 divided by 3. Okay, you will get the answer as 1333.33 mm. Okay, x1 bar. Similarly, A2 area of rectangle 2. Okay, here width of the rectangle is 2000 mm and height is 30 into 10 power 6. 30 into 10 power 6. Okay, therefore it is B into D. Area B is 2000 and depth is 30 into 10 power 6. Okay, answer is 6 into 10 power 10. Then x2 bar. What is x2 bar? Distance of centroid of rectangle 2 from nearest support. How much it will be? X2 bar from here to here. You need the distance, correct? So from this dotted line, it will be a distance of 2000 divided by 2 means 1000 mm. Okay, this 1000 plus 2000, you will get 3000. Okay, from nearest support. So it will be 2000 plus 2000 divided by 2 means b by 2. We will get the answer as 3000 mm. Okay, then coming to area 3, area of rectangle triangle 3, again of BH half into base into height, half into base is 2000. So you need to calculate the height. What will be the height, students, here? What will be the height? Here 40 minus 30, you will get 10 into 10 power 6 as height of this component 3. Okay, so 10 into 10 power 6. 10 into 10 power 6. Okay, so answer is 1 into 10 power 10 is the area 3. Similarly, x3 distance of centroid of rectangle 3 from nearest support. Okay, from here to here 2000, 2000 plus 2b by 3. 2 into 2000 divided by 3 will give x3 bar, correct? Therefore, here it is 2000 plus 2b by 3, nothing but 2000 plus 2 into 2000 divided by 3. So the answer you get is 3333.33. Okay, this is x3 bar. Okay, now you can easily find deflection due to the live load. Therefore, deflection due to live load is equal to a1 x1 bar 3 into 10 power 10 into x1 bar 1333.33 plus a2 x2 bar 6 into 10 power 10 into x2 bar 3000 plus a3 x3 bar 1 into 10 power 10 into 3333.33 whole divided by EC into IX. EC is how much? EC 35 into 10 power 3 into 337.5 into 10 power 6. Let me write the same thing here. 35 or 38 it is. It is 30. Let me check here. Here I took 38. Yes, see, they have given 38 only now. So let me change the value here. It is 38. 38. Okay. Let me write the same value here. Answer is same. Okay. Answer is same only. 4.49 mm only you will get. Okay. While writing, instead of taking 38, I took 35 at the beginning. Okay. But the answer which you get is same only. Okay. So here 38 into 10 power 3 into 337.5 into 10 power 6. By this you will get deflection due to live load. How much you will get is 19.75 millimeter. 19.75 millimeter. Okay. Now we have determined deflection due to dead load, that is 4.49 millimeter. We have also determined deflection due to live load. We got it as 19.75 mm. Similarly, we will find deflection due to prestress. Third point, deflection due to prestress. C, deflection due to prestress. Deflection due to prestress. Okay, just look into the cable profile. What is the cable profile? Part of the cable is above the central axis and part of the cable is below the central axis. What is the nature of diagram then? Here. Yes, this is what the nature of diagram which you have to take for the calculation of deflection due to prestress. Okay, here you can see part of the cable is above the central axis of support and part of it is below central axis. So these two diagrams you need to write here. Okay, let me write the same diagrams here. Okay. Now this first diagram is for the cable portion which is above the central axis. Okay. So here the equation will be P into E1. Okay. We'll call this as P into E1. We will resume the class. Yes. So here this first diagram is for the cable profile which is above the axis. Okay, if it is above the axis, the sign is plus. Okay. So this eccentricity at the support, if we consider as E1, and eccentricity at the midspan, if we consider as E2, here for first diagram it is P1, P into E1, P1. So prestressing force is given, it is 350 kilonewton, nothing but 350 into 10 power 3 Newton. So eccentricity at the support is 25. Okay, we will get the answer as 8.75 into 10 power 6. 8.75 into 10 power 6. Then P into E1 plus E2 here. Okay, as per this diagram, P into E1 plus E2. So P into E1 plus E2 is 350 into 10 power 3 into E1 plus E2 is 25 plus 75. So the answer is 35 into 10 power 6. 35 into 10 power 6. Now draw the central axis here. Now half of the diagram we have to consider for the calculation. Okay. Now here let us consider this as component number 1 and this is component number 2, and we'll mark the x1 bar and x2 bar also. So here it is x1 bar and x2 bar. Okay, and this length is how much here? This length. See, total length of the beam is 8 meter. I think about 8,000 mm. So half of it is 4,000 mm. 4,000 mm. Here also it is 4,000 mm. Okay. Now we can find the deflection using these diagrams. Deflection due to prestressing force is equal to. So what about the sign here? See, the portion of the cable at the midspan is below the central axis. So sign is negative here. Sign is negative. Now, if you first you write the generalized formula, area into x bar divided by EC into Ix is the generalized formula. Expand this. Yes. Expand this formula. Check ಏನ್ ಮಾಡ್ತೀಯಪ್ಪ ನೀನು ಹೇಳು. Hey, mute the audio. Who is that? Mute the audio. Who is talking? Navneet. Mute the audio. Area into x bar divided by c into ix. Expand this formula. So for this parabola, sign is negative minus a1 x1 bar. For this rectangle, sign is plus a2 x2 bar plus a2 x2 bar whole divided by ec into ix. Now find a1. A1 is what is the area of parabola? 2/3 of b into h. 2/3 of b into h. 2/3 of b is 4,000 and h is 35 into 10 power 6. Answer is 9.33 into 10 power 10 mm square. Okay. Then x1 bar will be, you know the formula for finding the centroid of parabola, that is 5 by 8 of b. Nothing but 5 by 8 of 4,000. Okay, we'll get the answer as 2,500 mm. Then A2. A2 means area of rectangle 2. Width is 4,000, depth is 8.75 to 10 power 6. B into D, 4,000 into 8.75 into 10 power 6. So you'll get the answer as through 3.5 into 10 power 10. All of you check the answer. X2 bar will be B by 2. 4,000 divided by 2. You'll get the answer as 2,000. Half of the base width. Correct? 2,000 mm. Now you can substitute everything and you can get the deflection due to prestress or prestressing force. Therefore, delta P is equal to minus A1 x1 bar minus 9.33 into 10 power 10 into x1 bar 2,500 plus A2 x2 bar, that is 3.5 into 10 power 10 into x2 bar 2000 whole divided by A1 plus A2. Sorry, whole divided by EC into IX. EC and IX values will be the same, that is 38 into 10 power 3 into 337.5 into 10 power 6. Okay. Therefore, if you calculate the deflection due to prestressing force, you will get the answer as minus 12.73 mm. Okay. This negative sign indicates what? It is causing upward deflection to the beam. Okay. Here, positive sign indicates that live load is causing downward deflection of the beam. And here also, for deflection due to dead load, it is positive. Positive sign indicates the dead load is causing downward deflection to the beam. Okay. Now just go to the question. Neglecting the losses of prestress, estimate the short-term deflection due to self-weight and the prestress. Okay. Short-term deflection due to self-weight plus prestress we have to find. Okay. Now first question, short-term deflection. First question, short-term deflection. Short-term deflection short-term deflection. It is asked to find only deflection due to self-weight and the pre-stress. Correct? Short-term deflection due to self-weight and pre-stress. Short-term deflection due to self-weight and pre-stress is equal to deflection due to dead load, that is self-weight, plus deflection due to pre-stressing force. Deflection due to dead load is how much? It is 4.49 minus 12.73 deflection due to pre-stress. What will be the answer? Just calculate. It is 4.49 minus 12.73. It is minus 8.24 mm. Minus 8.24 mm. Okay. This minus sign indicates the deflection in upward direction. Okay. So actually short-term deflection we will calculate including the deflection due to live load, but it is specifically mentioned in the question. Okay. Specifically mentioned in the question, that is estimate the short-term deflection due to self-weight and the pre-stress. Means we have to consider only self-weight deflection and pre-stress deflection for the calculation. If required, we can calculate the one more short-term deflection including all dead load, live load and pre-stress. Short-term deflection due to self-weight plus pre-stress plus live load. So this also you can calculate, that is delta DL plus delta PS plus delta LL. Okay, delta DL plus delta PS value is minus 8.24. I will directly write that answer. Plus delta live load is how much we got? We got it as 19.75. 19.75 mm. So final answer will be plus 19.75. We have to calculate 19.75. So answer is 11.51 mm. 11.51 mm. Positive sign indicates the deflection is in downward direction. So this is short-term deflection considering self-weight, pre-stress and the live load. Okay. Then coming to the second question. So in the notes, I have calculated this Deflection due to self-weight prestress and the lay load in the notes, students. I have not calculated the deflection due to only the self-weight and the prestress, that you can make it. Okay. Next, moving to the second question, that is asked to find allowing for 20% loss of prestress, estimate the long-term deflection under prestress, self-weight and the lay load. Okay, creep coefficient is given as 1.8. So we know the formula for calculating the short-term long-term deflection. Second one, long-term deflection. Second question, long-term deflection. Delta is equal to, we have the formula, delta IL plus delta IP into loss ratio into 1 plus creep coefficient. This is the formula we have. So where delta IL is deflection due to loads. Deflection due to loads, that is including dead load and the lay load, that is delta DL plus delta LL. Delta DL is 4.49 plus delta LL is 19.75. If we calculate the answer, it is 24.24 mm. Then delta IP is what? Deflection due to prestressing force. Deflection due to prestress, that we have already calculated, due to prestress, that is how much we got, that is minus 12.73 mm. Delta PS is equal to minus 12.73 mm. Okay. What about the loss ratio? He said that 20% loss, considering the 20% loss of prestress. Okay. So 20% loss means what will be the loss ratio? 20% loss is nothing but there is 20 Newton per mm square loss out of 100. Okay. So out of 100, if there is 20% loss, then the final prestress will be how much? Okay, 20, he says 20% loss. 20% loss means in 100 Newton per mm square of initial prestress, 20 Newton per mm square will undergo loss. So the final prestress will be 80. Okay. Loss ratio is nothing but it is PF by PI. Loss ratio is the ratio of final prestress divided by initial prestress. Final prestress will be how much? After 20 MPa loss, final prestress will be 80. 80, initial prestress will be 100. You will get loss ratio 0.8. So I'll write this as 1 minus 20 by 100. Okay. So you'll get the answer as 0.8 as loss ratio. Nothing but this is nothing but loss ratio. Okay. And creep coefficient is given. Creep coefficient pi, it is given as 1.8. 1.8, you will get the short term, long term deflection. We can calculate easily. Delta IL is 24.24 plus delta IP is minus 12.73 into loss ratio 0.8 into 1 plus pi plus 1.8. By this we'll get the long-term deflection. If we calculate, we'll get the answer as 39.36 mm. All of you check the answer. This is what the answer for the second question. Okay. So to this, this problem is over. If you have any doubts at any steps, you can ask students. I hope this is clear for everyone. We will move on to the next problem. Sixth problem. Please write the problem number 6, all of you, quickly. Go through the question. A concrete beam with a rectangular section 300 mm wide and 500 mm deep. Okay. The cross section is given. How much it is given? 300 mm wide and 500 mm deep. Okay. Is prestressed by two post-tensioned cables of area 600 mm square each. There are two cables having 600 mm square area which are provided in the beam. Okay. Now you can calculate the area of cables. Therefore, area of cables is equal to, he says that is tested by two post-tensioned cables of 600 mm square area. Okay, there are two cables each having 600 mm square area. Therefore, it is 2 into 600. So you will get the area of cables as 1200 mm square. Okay. The cables 600 mm square each, initially stressed to 1600 Newton per mm square. Initial pre-stress is given. Initial pre-stress. Initial pre-stress. It is given as how much? 1600 Newton per mm square. Okay. See, area of cable is given. Pre-stress in the cable is given. So pre-stress multiplied by area will give pre-stressing force. Correct. Therefore, pre-stressing force P is equal to stress into area. Okay, stress is 1600 into area of cable is 1200. If you calculate the answer, you will get the answer as 1.92 into 10 power 6 Newton as pre-stressing force, or else 1.92 into 10 power 3 kilonewton. Okay, then go through the problem. The cables are located at a constant eccentricity of 100 mm. Constant eccentricity of 100 mm is equal to 100 mm. Constant eccentricity of 100 mm throughout the length of the beam having a span of 10 meter. Length of the beam is given. L is equal to 10 meter, nothing but 10,000 mm. Okay. The modulus of elasticity of steel and concrete is 210 and 38 kilonewton per mm square respectively. Okay. So EC, ES means Higgs modulus of steel is how much it is given? 210 kilonewton per mm square. 210 kilonewton per mm square, which is nothing but 210 into 10 power 3 Newton per mm square, and EC, it is given as 38 kilonewton per mm square, nothing but 38 into 10 power 3 Newton per mm square. Okay. Neglecting all losses, the question coming to the question, neglecting all losses, find the deflection at the center of span when it is supporting its own weight. Okay, when it is supporting its own weight, you have to find the deflection at the center of the span. Then second question, allowing 20% loss in pre-stress, find the final deflection at the center of the span when it carries imposed load of 18 kN per meter. Okay, density of concrete is given as 24 kN per meter cube. It is almost similar to the previous problem only, correct? But the loading condition given here is different. Okay, it is imposed, it is carrying an imposed load of 18 kN per meter. Okay, UDL is given. Okay, follow the same procedure whatever you have followed for the previous problem. Okay, first you find deflection due to self-weight or deflection due to dead load. A, deflection due to self-weight. Okay, delta DL. Therefore, delta DL is equal to, we have the formula 5 by 384 W L raised to 4 by EC into IX, where W is intensity of the self-weight, that you can find, correct? Self-weight or dead load is equal to area cross-sectional area multiplied by density. Cross-sectional area is given, how much it is given? 300 by 500, nothing but 0.3 into 0.5 into 24. Okay, density of concrete. The answer is 3.6 kilonewton per meter or 3.6 Newton per millimeter. Okay. Now, deflection due to dead load you can calculate, that is 5 by 384 into 3.6 length of the beam. How much it is given? Length of the beam. Okay, it is 10,000 mm. 10,000 4 raised to 4 divided by EC into IX. EC is given as 38 into 10 power 3. IX, we can find it. IX is equal to BDQ by 12. So B is 300, D is 500 cube by 12. So if you calculate, you will get the answer as 3.125 into 10 power 9. 10 power 9 mm4. Okay, IX. Therefore, here 3.125 into 10 power 9. Okay. Therefore, deflection due to dead load, if we calculate, the answer will be 3.95 mm. Plus sign indicates deflection is in downward direction. Okay. Now, what next after finding the deflection due to self-weight? Deflection due to pre-stressing force you find, or deflection due to live load you can find. Okay. Deflection due to live load only you find. B, deflection due to live load, delta LL. Deflection due to live load. Okay. Therefore, deflection due to live load, delta LL is equal to 5 by 384. See, intensity of the live load is UDL only. Okay. He says that it is UDL only. How much it is? 18 kilonewton per meter. Kilonewton per meter means 18 Newton per millimeter. Span is 10 meter. So for beam carrying UDL, deflection due to live load is 5 by 384 WL raised to 4 by EC into IX only. Same formula. So 5 by 384, 5 by 384, W is 18 into length of the beam is 10,000. 10,000 raised to 4 divided by EC 38 into 10 power 3 into IX 3.125 into 10 power 9. By this you will get deflection due to live load. Okay. So the answer which you get is 19.73 mm. 19.73 mm. Okay, this is deflection due to live load. What next? Calculation of deflection due to prestress. C. Deflection due to prestress. Deflection due to prestress. So just look into the cable profile. Cable profile, he says that the cables are located at a constant eccentricity of 100 mm throughout the length of the beam. Okay, let me write the diagram. So this is a beam and this is the central axis. Central axis. And he says that the cable is located at a constant eccentricity of 100 mm throughout the length 100 mm. Okay. Okay. Now for this you need to write the bending moment diagram for the cable carrying the cable having profile constant eccentricity throughout the length. At the beginning only we have see here for cable carrying constant the cable having constant eccentricity throughout the length of the beam. This is what the nature of the BMD. Okay. So as the cable is below the central axis, sign is negative here. Okay, minus PE. Okay. Now the diagram will be negative sign here minus PE. PE is prestressing force we have calculated already. It is 1.92 into 10 power 6 Newton. 1.92 into 10 power 6. Eccentricity is given is 100 mm. 100 mm. It will be how much? 192 into 10 power 6. Okay. Now divide this figure into half. Okay. So here total length of the beam is given as 10,000. So this length will be 5,000. Base width of the rectangle will be 5,000. And if we take G as centroid, so this is the X1 bar. That is 5,000 divided by 2. Okay. Therefore, deflection due to prestress is given by sign is negative. So minus area into X bar, generalized formula area into X bar divided by EC into IX. So there is only one area. So minus is the negative sign, minus is the sign. Minus A1 into X1 bar divided by EC into IX. Okay. A1 will be 5,000 is the width and 192 into 10 power 6 the depth. Therefore, it is 5000 into 192 into 10 power 6. If we calculate, you will get the answer as, I don't have the answer here. Let me calculate 5000 into 192 into exponential 6. 0.6 into 10 power 11. X1 bar is equal to B by 2. That is 5000 divided by 2, 2500 mm. Okay. Therefore, delta PS deflection due to prestress is equal to minus 9.6 into 10 power 11 into x1 bar 2500 divided by EC into IX. EC is 38 into 10 power 3 into IX. Just before we have calculated the IX 3.125 into 10 power 9. 10 power 9. Okay. So if you calculate the answer, you'll get the deflection due to prestress as minus 20.2 millimeter. Negative sign indicates what? Deflection is in upward direction. Deflection is in upward direction. Okay. Now coming to the questions. What is the first question? First question is neglecting all losses, find deflection at the center of the span when it is supporting its own weight only. Okay. Excluding the layer load, we have to find the net deflection. Question A or question first question. Yes, question A we will solve. Okay, no problem. Question A. So net upward deflection. Net upward deflection is equal to. So we have to find net upward deflection. Only it is supporting when it's supporting its self weight. Okay, self weight and the prestress. Okay. So excluding the line load, we have to find the deflection. Excluding the line load, we have to find the deflection. Okay. Deflection due to, which is nothing but deflection due to dead load plus deflection due to prestress. Okay, excluding the deflection due to line load, we have to find the net upward deflection. He clearly says in the problem, when it is supporting its own weight, that's it. You have to find the deflection at the center of the span when it is supporting its own weight. Okay. Delta dead load, how much it is? 3.95 minus 20.2. Okay. So it is minus 16.26 mm. Negative sign indicates upward deflection. Okay. Now, second question. Allowing 20% loss in prestress, find the final deflection at the center of the span when it carries an imposed load of 18 kN per meter. Here we have to add, we have to take into consideration of imposed load, deflection due to imposed load while calculating the total deflection. Okay, and one more point is added here, considering 20% of the loss of prestress. Okay, considering 20% of the loss of prestress, we have to find final deflection at the center of the span when it carries an imposed load of 18 kN per meter. So here two things are added. First thing is 20% loss is there in the pre-stressing force, and one more thing, there is live load of 18 kN per meter. Including these, considering these two factors, we have to identify, we have to calculate deflection. Means what you have to do is you have to find deflection due to pre-stress considering 20% loss of pre-stress. Means this pre-stress value, you know, P value, pre-stressing force value, how much it is? 1.92 into 10 power 6. In this, we need to reduce this value by 20%, and for that prestressing force, we need to calculate the deflection due to prestress. Okay. And we have to calculate deflection due to live load that we have already calculated. Okay. Now, there is one easiest way to calculate deflection due to prestress by considering the loss. Okay. Now we have already calculated deflection due to prestress with 192 into 10 power 6 as the prestressing force value. You got it as 20.2 mm. When you consider the loss of prestress, means when you reduce this prestressing force, okay, prestressing force by 20%, means for 80% of this 182 into 10 power 6 force, if you calculate the deflection, this deflection will also reduce by 20%. Means only you will get the deflection due to prestress as 80% only, 80% of this obtained value, that is 20.2 mm only. So instead of calculating once again, so you reduce this value by 20%. Means for 80% of the value you calculate. That will be the answer. Okay, I hope you are understanding. Considering, elaborate, considering question B we are solving now. Considering 20% loss of prestress, 20% loss of prestress, that is 100 minus 20. That is 80% only the left out prestressing force. Nothing but 80 by 100, you will get 0.8. Okay. So you need to calculate the deflection due to 80% of the prestressing force. If you calculate deflection due to 80% of the prestressing force, you will get 80% of this obtained 16.26 only. Okay. So directly you calculate 80% of this 16.26, that will be the value for 80% of the prestress. Deflection due to 80% of the prestress. Okay. Therefore, upward deflection due to pre-stress after loss will be 80% of this value, 0.8 into 16.26. Sorry, 20.2. Sorry, 20.2 minus 20.2. So you'll get the answer as minus 16.16 mm. So upward deflection due to prestress will be reduced now. That is an indicates upward deflection. Okay, now you can calculate the total deflection. Therefore, total deflection is equal to the sum of deflection due to dead load, deflection due to live load plus deflection due to pre-stressing force after considering 80% loss, that is 16.16. Don't take this 20.2 mm. It is for 100% pre-stressing value. For 80% pre-stressing value, deflection will reduce by 20%. Means 80% of the 20.2 means 16.16 mm you will get. Deflection due to dead load, how much you got? It is plus 3.95 plus 19.73. 3.95 plus 19.73 minus 16.16. Okay, the answer, final answer will be 7.52 mm. 7.52 mm. Okay, so this completes the second question. Okay, this problem is also over. Any doubts you can ask before moving on to the next problem. Okay, thank you. Next problem, all of you write. Go through the problem. A concrete beam with cross-sectional area 32 into 10 power 3 mm square. Okay, cross-sectional area is given. How much it is given? It is 32 into 10 power 3 mm square. And radius of gyration of 72 mm. Now new term has come, that is radius of gyration. Radius of gyration. Radius of gyration. R it is given. And it is given as how much? It is given as 72 mm. 72 mm is pre-stressed by a parabolic cable carrying an effective stress of 1000 Newton per mm square. Okay, stress is given. Pre-stress. Pre-stress is given as 1000 Newton per mm square. Okay, 1000 Newton per mm square. The span of the beam is 8 meter. Length of the beam is given. It is given as 8 meter. L is equal to 8 meter, nothing but 8000 mm. Okay. The cable is composed of 6 wires of 7 mm diameter, has an eccentricity of 50 mm at the center and 0 at the support. It is a parabolic cable only. Okay, having 50 mm at the center and 0 eccentricity at the support. Okay. Now, how many number of cables are given? There are 6 wires. Okay, having 7 mm diameter. We can calculate the total area of the cable. Area of cable is equal to area of one wire will be pi d square by 4, pi into 7 square by 4 into there are 6 numbers of wires. By this we'll get total area of the cable, that is 230.9 mm square. Okay, so area of cable is given, pre-stress in the area, pre-stress in the cable is given, stress multiplied by area will give pre-stressing force. Therefore, pre-stressing force is equal to pre-stressing force is equal to stress multiplied by area. Pre-stress is 1000. Area is 230.9. 230.9. Therefore, the answer is 230.9 into 10 power 3 Newton. This is P. Okay. Now, area of the section is now given. Radius of gyration is given. Using these two data, okay. Using these two data, you can find the moment of inertia. You can see that the length, okay, width and depth of the beam is not given, not mentioned here in the problem. Indirectly, the moment of inertia is given. How indirectly given? Area of cross section, total area of cross section of the rectangular section is given, and radius of gyration is given. We have the formula for radius of gyration. We know that Radius of gradation R is equal to what is the formula? Root of I by A. This you learnt in your first year of engineering itself. Root of I by area of cross section is given. Area of cross section of the member 32 into 10 power 3. 32 into 10 power 3. Okay. So radius of gradation it is given as 72 mm. By this you can work out the moment of inertia. If you work out the answer, you will get it as 165.88 into 10 power 6 mm 4. Okay, this will be the answer. Okay. Now the question is to find the deflection due to sulfate and prestress, and deflection due to sulfate, prestress, and line load of 2 kN per meter. Initially find all the deflections due to sulfate, prestress, and the line load. Then adding together, we will get the answers. First one, deflection due to sulfate. Deflection due to sulfate. Delta DL. Okay. So sulfate, you can find it, correct? Sulfate of the beam cross-sectional area is given. Cross-sectional area is given. Then you can find the sulfate, correct? Sulfate is equal to cross-sectional area multiplied by density. Cross-sectional area, how much it is given? 32 into 10 power 3 mm square. 32 into 10 power 3 mm square. But we need to substitute here area in terms of meter square. So mm square you convert into meter square. 1 mm is equal to 10 power minus 3 m means 10 power minus 3 meter whole square into 24. Okay, I hope you understood. Therefore, sulfate intensity you will get it as 0.768 kilonewton per meter or 0.768 Newton per millimeter if you convert into Newton per mm. Okay. Now deflection due to dead load. Therefore, deflection due to dead load. What is the formula? 5 by 384 W L raised to 4 by EC into IX. Everything is now just substitute 5 by 384 into W is 0.768 into length of the beam 8 meter 8000 mm 4 8000 raised to 4 divided by EC into IX. EC is it given? Young's modulus of concrete. I think it is not given, though it though it is not given, you need to assume what is the standard value which we used for the previous problems. It is 38 into 10 power 3. And moment of inertia just before we have calculated, that is 165.88 into 10 power 6 into 10 power 6. Therefore, deflection due to dead load is equal to 6.49 millimeter. Positive sign indicates it is causing downward deflection in downward direction. Next, deflection due to pre-stress or deflection due to live load you find. Deflection due to live load delta LL. Okay. Now, live load intensity, how much it is given? It is given as 2 kN per meter. Means it is a UDL only. Okay, it is a UDL only. Two kilonewton per meter. 8 meter is the span. So therefore delta live load. Okay, for the beam carrying UDL is Same formula 5 by 384 WL raised to 4 by EC into IX. Same values except the load. 5 by 384 into 2 into 8000 raised to 4 divided by 38 into 10 power 3 into 165.88 into 10 power 6. Therefore, deflection due to live load, if we calculate, so it will be 16.92 mm. 16.92 mm. Positive sign indicates deflection is in downward direction. Okay. Then third one, deflection due to live load. C, deflection due to live load. Sorry, deflection due to prestressed, no? Prestress delta PS. Okay. To calculate deflection due to prestress, just look into the cable profile. How the cable profile is given. Has an eccentricity of 50 mm at the center and 0 at the support. And he says that it is a parabolic cable. It is a parabolic cable. Okay, let me write the diagram. Centroidal axis. Parabolic cable with 0 eccentricity at the support, 50 mm eccentricity at the center. E is equal to 50 mm. Okay. Let me go to the theory part. See what is the nature of bending moment diagram for cable having 0 eccentricity and some eccentricity at the midspan. This is what the nature of bending moment diagram. And sign will be negative because cable is below the central axis only. Correct? No. Toward the figure. Here what will be the value? PE. Negative sign. P into E. Pre-stressing force is how much you got? Pre-stressing force 230 into 10 power 3 Newton. 230 into 10 power 3. Eccentricity is 50 mm. 50 mm. So the answer is 11.54 into 10 power 6. Okay. X1 bar. Same procedure here also. Therefore, delta PS is equal to area into X bar divided by EC into IX. So minus A1 X1 bar divided by EC into IX. Therefore, A1 is equal to 2/3 of base into height. Base is how much? Base width. Total length of the beam is how much it is given? Total length of the beam 8 meter. So 8 meter, half of 8 meter is 4 meter, nothing but 4000 mm. 4000 mm. So 2/3 of 4000 into height is 11.54 into 10 power 6. 11.54 into 10 power 6. Therefore, A1 You will get how much you will get. Let me calculate. I don't have the answer here. 2 into 4000 into 11.54 into exponential 6 divided by 3 divided by 3. 3.07 into 10 power 10. Then x1 bar will be 5 by 8 of b. 5 by 8 of 4000. 4000. So answer is a into 4000 divided by 8. 2500. Therefore, delta PS is equal to minus 3.07 into 10 power 10 into 2500 divided by EC into IX. That is 38 into 10 power 3 into 165.88 into 10 power 6. If we calculate the answer, it will be minus 12.2 mm. Okay, negative sign indicates deflection is in upward direction due to prestress. Okay, then coming to the question, there are two questions to find the deflection due to self-weight and prestress. Question number A. Question number A. Deflection due to self-weight plus prestress is equal to delta DL plus delta PS is equal to delta DL is 6.49, 6.49 minus 12.2. Okay, that is 5.7 mm. Positive sign indicates net deflection is in upward direction. Second question, self-weight plus prestress plus live load. Okay, self-weight is 6.49. That's nothing but delta dead load plus delta PS plus delta live load. Delta dead load is 6.49 minus 12.2. Due to live load, deflection is plus 16.92 plus 16.92. If we calculate the answer, you'll get it as 11.21 mm. And this positive sign indicates it is the deflection is in downward direction. Okay. So this completes the problem. And there is problem number 8. You take this as homework. Okay. Take this as homework. And I have provided the answers in the notes. Okay. You can just cross check the answers. Okay. Students, I'll be back in 1 minute. Okay, we'll end the class for today, and we'll continue the next class. Okay.